In November 2026, a radio command sent from Earth toward Voyager 1 will begin a journey that lasts almost an entire day. The signal will travel at the speed of light, crossing billions of kilometers of darkness before it reaches a machine launched nearly half a century earlier. If Voyager answers, its reply will need almost another day to return. A simple exchange between Earth and its most distant spacecraft will take nearly 2 days, even though nothing in between is slowing the signal down. That delay gives us the clearest way to feel Voyager's distance. By this point, the spacecraft is about 171 times farther from the Sun than Earth is. It is more than 25 billion kilometers away, moving outward at almost 17 kilometers every second. In a single year, it covers roughly 3.5 times the distance between Earth and the Sun. By any human measure, Voyager 1 has traveled unbelievably far. No journey offers a comparison. The distance is so great that controllers cannot watch the spacecraft respond in real time. Every instruction must be sent toward the position calculations say Voyager will be when the command arrives. Then the team waits. For nearly a day, nobody can know whether the machine has received the message. For another day, nobody can know how it responded. The spacecraft remains connected to Earth, but only through a conversation stretched across billions of kilometers. That connection makes Voyager feel both present and almost unreachable, still within human history, yet already separated from us by the travel time of light itself. On a map of the solar system, it appears to have escaped everything familiar. The planets lie behind it. The Sun has faded into an unusually bright star. Earth is too distant to see as a separate world. Voyager seems to be doing exactly what its popular image suggests, leaving the solar system behind and flying in a straight line into interstellar darkness. But that image is incomplete. Voyager is moving away from the Sun, yet away does not tell us where it will ultimately go. Its current speed does not remain the only motion that matters. The Sun itself is moving. Nearby stars are moving. The entire stellar neighborhood is circling the center of the Milky Way. Voyager is part of that larger motion too, whether or not it has escaped the Sun. The distance it has covered is enormous compared with any earlier human journey, but tiny compared with the regions that will shape its future. Light needs almost a day to reach it now. Light will need years to cross the distances between the stars it may pass. The spacecraft will spend thousands of years moving through the Sun's distant outskirts, millions of years drifting among changing stellar neighborhoods, and billions of years following the gravity of the galaxy. At each stage, the meaning of its location will change. Today, we describe Voyager by its distance from Earth or the Sun. Later, its position will make more sense relative to passing stars. Far beyond that, only its orbit inside the galaxy may remain useful. Eventually, even that orbit will become impossible to predict precisely. So the real mystery is not simply how far Voyager will travel. It is what will hold it when the Sun no longer does, how its path will change as one gravitational system gives way to another, and what kind of answer science can honestly provide after 10 trillion years. Voyager is almost 1 light day away, yet on the scale of its true journey, it has barely begun. The first step toward answering that question is to decide what the word "where" actually means. For an object on Earth, location seems simple. We can name a country, a city, or a point on a map. But Voyager is not resting on a surface. It is moving through a collection of moving systems, each contained inside something larger. From Earth, Voyager appears in the direction of Ophiuchus. That name helps astronomers point antennas toward the correct patch of sky, but it does not describe a destination. A constellation is a pattern seen from our present viewpoint. Its stars do not form one fixed structure in space, and they will not preserve the same pattern forever. They travel along their own paths while the Sun and Voyager move as well. Saying Voyager is heading toward Ophiuchus is therefore like naming the direction in which a ship leaves a harbor. It tells us where to look now, not where the journey must end. We can also describe Voyager's position relative to the Sun. This is the most useful frame for its current escape because it shows the spacecraft increasing its distance from the center of the solar system. In that frame, Voyager is clearly moving outward. Solar gravity continues to pull on it, but the spacecraft has enough motion to keep escaping rather than falling back into a closed orbit. Yet the Sun is not standing still. It moves through the Milky Way, along with the planets, comets, and nearby stars. Voyager shares much of that larger galactic motion because it began inside the solar system. Its departure added a smaller motion relative to the Sun. It did not erase the movement it already shared with the Sun around the galaxy. This creates several correct descriptions at the same time. Relative to Earth, Voyager is a distant spacecraft whose radio signal requires an extraordinary delay. Relative to the Sun, it is an escaping object moving toward interstellar space. Relative to nearby stars, it is one small body passing through a neighborhood in which every possible landmark is also moving. Relative to the Milky Way, it remains part of a vast population circling the galactic center. None of these descriptions cancels the others. Each answers a different version of the same question. The important difference is not merely the map being used, but the gravity that controls the motion on that map. An object can leave one gravitational system without leaving every larger system around it. A stone thrown from a small moon might escape that moon while remaining captured by the planet the moon orbits. In the same way, escaping the Sun does not automatically give Voyager enough speed to escape the Milky Way. Freedom from one orbit can mean entrance into another, much larger one. That is why the title's question cannot finally be answered with a single coordinate. Over the near future, Voyager's path can be calculated with impressive accuracy. Its position and speed are known well enough for Earth to aim a narrow radio signal across billions of kilometers. As the timescale grows, however, the question changes. Instead of asking for an exact point, we must ask which region Voyager probably occupies, which gravitational system still contains it, and what physical state the spacecraft is likely to have reached. Every coordinate belongs to a chosen frame. Give Voyager's distance from Earth, and Earth has already moved before it is spoken. Give its distance from the Sun, and that describes only one relationship inside a galaxy that is turning. Name the closest star, and that star may be passing rather than becoming a permanent neighbor. Even a position within the Milky Way describes one moment in a galaxy whose stars continue to circle, scatter, and rearrange. The farther ahead we look, the less useful a frozen map becomes. What remains useful are relationships. Whether Voyager is approaching or receding, whether an encounter can bend its path, whether its speed is enough to escape, and whether a larger structure still keeps it bound. Those questions follow the forces shaping the journey, instead of pretending the surrounding universe remains fixed. This is not a weaker kind of answer. False precision would give us a confident point on a map that future events could easily erase. A scientifically useful answer must separate what can be calculated from what can only be estimated, and what no responsible model can promise at all. For now, the most important fact is that Voyager is not traveling across a motionless background. Its apparent direction changes meaning as the Sun, the stars, and the galaxy continue their own journeys. Before we can follow Voyager through those larger systems, we need to understand how it acquired the path that is carrying it away from the Sun in the first place. That path was not created by an engine burning without end. Its decisive shape was established decades ago, during a short series of encounters with giant planets. The route Voyager follows today, and the journey it may continue for trillions of years, began with choices made in 1977. Voyager's escape did not begin with an engine powerful enough to push it toward the stars. It began with timing. When Voyager 1 launched in 1977, its rockets gave it the speed needed to leave Earth and begin crossing the solar system. But the launch alone did not create the path it follows today. The decisive changes came later, when the spacecraft passed close to Jupiter and Saturn. Voyager is often imagined as a machine continually driving itself forward, like an aircraft crossing an endless sky. In reality, most of its journey is a coast. Its small thrusters can control orientation and make limited corrections, but they do not provide the steady push carrying it away from the Sun. Once the spacecraft had gained its escape trajectory, motion and gravity did the rest. The key was the gravity assist. A planet moving around the Sun carries an enormous amount of momentum. As a spacecraft approaches, the planet's gravity pulls it inward and bends its path. The spacecraft accelerates while falling toward the planet, then slows as it climbs away. If the planet were standing still, the spacecraft would leave with roughly the same speed with which it arrived, only traveling in a different direction. But a planet is not standing still. It is racing around the Sun. By approaching from the correct direction and passing along a carefully chosen path, a spacecraft can exchange a tiny amount of momentum with that moving planet. The planet's own motion changes the spacecraft's speed relative to the Sun. The planet loses an immeasurably small fraction of its momentum, while the lightweight spacecraft receives a major change in speed and direction. Nothing is created for free. The energy comes from the planet's orbit, although Voyager takes so little that the effect on the planet cannot matter in practice. What matters is geometry. Arrive too early, too late, too high, or too low, and the same encounter produces a different route. The useful path exists only because the spacecraft and planet reach the meeting point at the right time. This made navigation part of propulsion. Controllers did not simply aim Voyager at Jupiter and hope gravity would accelerate it. They selected a path around it that would bend the spacecraft towards Saturn while giving it the required change in speed. The destination, arrival time, approach direction, and next encounter were connected. A correction made before one flyby could determine where Voyager passed the next planet later. The spacecraft therefore gained something no fuel tank aboard it could have supplied alone: access to the motion of worlds already traveling around the Sun. Jupiter provided the first great change. Its enormous gravity bent Voyager's course and increased its speed relative to the Sun, sending it onward towards Saturn. The encounter was not merely a way to visit another world. It was part of a connected route in which one planet delivered the spacecraft toward the next. Saturn then produced the turn that shaped Voyager 1's departure. The flyby redirected the spacecraft onto a path rising away from the broad plane in which most planets orbit. After that encounter, the essential direction of Voyager's long escape had been established. The mission would still make corrections and maintain its orientation, but no later engine burn would create its basic interstellar path. This is why a short event can control an immense future. Voyager spent only a small part of its existence close enough to the giant planets for their gravity to transform its journey. Yet the speed and direction created during those encounters remain built into its motion. Unless another object later passes close enough to disturb it, the spacecraft continues along the course those planetary meetings helped produce. The Sun has never stopped pulling on Voyager. Gravity does not end at a sharp distance. It weakens as the spacecraft moves farther away, but it continues trying to slow the outward motion. Voyager climbed away from the Sun, much as a thrown object climbs away from Earth, losing some speed as it moved outward. The difference is that Voyager was moving fast enough not to fall back. Its path around the Sun is not a closed ellipse like the paths of planets. It is an open escape path. As solar gravity becomes weaker, Voyager approaches a remaining speed that it would keep relative to the solar system if no other forces acted. This leftover motion after solar escape is called hyperbolic excess velocity. The term sounds complicated, but the idea is simple. It is the speed Voyager still has after paying the gravitational cost of climbing away from the Sun. That remaining speed is why no continuous engine is required. Voyager is not fighting to stay aloft, and there is almost no material in space to slow it through drag. It is following the consequence of its earlier motion. Every second carries it farther outward, while the Sun's ability to change that motion steadily diminishes. So Voyager's distant future began in a narrow period of opportunity. A launch from Earth placed it on the route. Jupiter added speed and redirected the journey. Saturn gave Voyager 1 the departure path that distinguishes it from the other outer missions. Human planning arranged the meetings, but after each encounter, gravity carried out the exchange. The result is genuine escape from the Sun. Voyager will not naturally turn around and return to a planetary orbit. Yet even this clear statement contains a hidden problem. The Sun's gravitational influence extends far beyond the region of the planets, and the phrase, "the edge of the solar system," can refer to more than one boundary. Voyager crossed one famous edge in 2012. That crossing made it the first human-built object to enter interstellar space. But it did not mean that every part of the Sun's domain was behind it. To understand how both statements can be true, we must separate the boundary made by the Sun's wind from the much larger region shaped by its gravity. The boundary Voyager crossed in 2012 was real. It was also only one of several possible edges of the solar system. For years before the crossing, Voyager had been traveling through the outer region of the heliosphere, the enormous bubble created by the Sun. The Sun constantly releases a flow of charged particles, called the solar wind. This wind spreads outward past the planets, carrying the Sun's magnetic influence with it. As it travels farther, it becomes thinner and meets material filling the space between the stars. The heliopause is the region where the outward pressure of this solar wind can no longer hold back the surrounding interstellar environment. It is not a wall, shell, or visible surface. Voyager did not pass through a bright line in the darkness. Scientists identified the transition through changes measured around the spacecraft. Particles connected with the Sun dropped sharply. High-energy particles arriving from beyond the heliosphere increased. Measurements of the local plasma and magnetic environment showed that Voyager had entered a region no longer dominated by the solar wind. By combining these changes, the mission team concluded that Voyager 1 crossed the heliopause on August 25, 2012. The conclusion did not depend on a camera seeing a border. Voyager's instruments acted like senses adapted to an invisible environment. They counted particles, sampled plasma, and recorded the conditions surrounding the craft. One reading alone might have been difficult to interpret, but several changes together revealed that the local balance had shifted. The spacecraft was still moving through darkness that looked empty, Yet the physical character of that darkness had changed. The crossing was defined by evidence carried back through Voyager's faint radio signal, not by the appearance of a visible landmark. That made Voyager the first human-built object known to enter interstellar space. The achievement does not become smaller when the boundary is defined carefully. For the first time, instruments made on Earth were directly sampling the space beyond the Sun's protective wind bubble. Voyager had moved from an environment created mainly by our star's outward flow into the material between stars. The confusion begins because interstellar space and outside the solar system are often treated as identical phrases. They are not always identical, because the edge depends on which part of the Sun's influence we are describing. One possible boundary is the region occupied by the planets. Beyond Neptune, the familiar planetary system is behind Voyager. Another boundary is the Heliopause, where the solar wind gives way to interstellar plasma. Voyager crossed that edge in 2012. A third boundary concerns gravity, how far the Sun can continue holding distant objects in long orbits. Gravity does not stop at the heliopause. The solar wind and solar gravity are different things. The wind is a stream of particles, whose pressure can be balanced by material outside it. Gravity is the attraction created by the Sun's mass. It grows weaker with distance, but it does not end where the solar wind ends. The planets show why these definitions cannot be compressed into one boundary. Their orbits occupy a relatively flat region, while the solar wind bubble extends much farther and changes shape as the Sun moves through surrounding space. The distant gravitational population is broader still. It is thought to surround the Sun in a vast distribution, rather than continue the familiar flat arrangement of the major planets. A map drawn to show planetary architecture, a map drawn to show plasma, and a map drawn to show bound icy bodies would therefore place the solar system's edge in different locations. Each map answers its own physical question. Far beyond the heliopause lies the region associated with the Oort Cloud, a vast and distant population of icy bodies thought to surround the solar system. These objects are not held together by the solar wind. They are connected to the Sun through gravity, moving along extremely large and slow orbits. The Oort Cloud cannot be drawn with a sharp inner and outer border. It is not a solid shell, and no spacecraft has reached it to map its structure directly. Its extent is inferred from the behavior of long-period comets and from models of how the solar system formed and evolved. Different estimates place its boundaries at different distances, so any single edge must be treated as approximate. This creates an apparently impossible statement that is actually precise. Voyager is in interstellar space because it has crossed beyond the heliopause. At the same time, it has not yet crossed the full distant region in which the Sun can hold small bodies. It has left the Sun's wind bubble while remaining deep inside the broader gravitational landscape associated with the solar system. The distinction becomes easier to understand if we imagine the Sun having more than one kind of reach. Its light extends outward. Its particle wind creates a limited bubble. Its gravity reaches much farther and becomes mixed with the influence of passing stars and the galaxy. These reaches do not share one common edge, because they are produced by different physical processes. Calling the heliopause the edge of the solar system is therefore useful when the subject is the solar wind. Calling the distant Oort cloud the outer solar system is useful when the subject is gravitationally bound material. Neither definition must defeat the other. The problem appears only when one kind of edge is presented as if every influence of the Sun ended there. This also changes the picture of Voyager's escape. The spacecraft did not pass through one final gate and enter a region with no connection to the Sun. Its journey is a gradual transfer between environments. Solar gravity continues weakening. The influence of the galaxy and passing stars becomes more important. There is no moment when every force belonging to one system switches off and another instantly takes control. The 2012 crossing marked a measured environmental change, not the completion of Voyager's entire departure. It answered one question: had the spacecraft passed beyond the region dominated by the solar wind? The evidence said yes. It did not answer a larger question: how long would Voyager remain within the Sun's distant gravitational outskirts? That larger journey has barely started. The region ahead is so wide that the Heliopause, despite its immense distance from Earth, appears close to the beginning. Voyager will need centuries merely to approach the inner part of the Oort Cloud and tens of thousands of years to pass beyond its broad outer region. That difference will shape everything that follows. So Voyager has crossed an edge, but not the only edge. It is the first spacecraft in interstellar space, yet it remains inside a much greater architecture shaped by the Sun. The next stage of its journey is not a quick exit into empty freedom. It is a passage through the most distant, least familiar outskirts of the system that launched it. Beyond the Heliopause, Voyager enters a journey measured not by mission years, but by centuries. The spacecraft is already farther from the Sun than any other human-made object, yet the inner region of the Oort Cloud may still be about 300 years ahead. Everyone alive today will be gone before Voyager reaches even that uncertain beginning. The number must be understood carefully. 300 years is not a scheduled arrival at a visible border. No marker waits there, and no instrument aboard Voyager will announce that the Oort Cloud has begun. Scientists estimate its inner region from models of the solar system and from the paths of long-period comets. Because those models allow a range of distances, the crossing time is also approximate. The same uncertainty applies to the cloud's outer extent. Its distant population may stretch from thousands to tens of thousands of times the Earth-Sun distance, with some estimates reaching farther. Depending on which boundary is chosen, Voyager's complete passage can be described differently. NASA's broad estimate is that the spacecraft will require roughly 30,000 years to travel beyond the cloud's outer region. 30,000 years is longer than recorded human civilization. Languages, borders, and cultures could appear and disappear while Voyager covers this remaining part of the Sun's outskirts. The spacecraft that crossed the outer planets within a few years of launch will spend hundreds of centuries moving through a region that is still associated with the system it left behind. Its speed has not suddenly become small. Voyager still crosses distances that would overwhelm any journey on Earth. The problem is that the scale around it has expanded. A pace that carried the spacecraft between planets within years becomes slow when the destination is measured across the remote gravitational territory of a star. This is the first major reversal in Voyager's future. The machine continues moving rapidly, but progress appears to slow because every meaningful landmark is farther apart. Nothing needs to stop Voyager for the crossing to consume thousands of generations. Distance alone creates the delay on its own. The same relationship will return on every larger scale. Between the Sun and its outer cloud, between one star and another, and eventually across the galaxy, Voyager's motion remains real, while the space ahead grows beyond the reach of familiar time. The word cloud can make this passage sound dangerous. It suggests a thick collection of objects surrounding the Sun, perhaps like fog or a field of debris. The likely reality is almost the opposite. The Oort Cloud may contain an enormous number of icy bodies, but they are spread across an even more enormous volume. The distances between them are expected to be vast. Voyager will not weave between closely packed comets. It will move through darkness, in which even a nearby Oort object would probably remain extremely far away. The chance of a direct collision is extraordinarily small, not because no objects exist, but because space increases much faster than the number of objects available to fill it. That emptiness is one of the central facts of Voyager's future. On diagrams, the Oort cloud must be compressed until it appears like a shell. In physical space, it is a thin population scattered through a region so wide that a spacecraft can spend tens of thousands of years crossing it without approaching anything closely. Voyager will also not travel through the cloud, as though entering a calm territory owned only by the Sun. At these distances, solar gravity is weak. It still contributes to the motion of distant objects, but the gravitational pull of passing stars and the broad field of the Milky Way can disturb their orbits. Those outside influences help send some long-period comets inward and may remove others from the solar system. For Voyager, the change in control will be gradual. There is no exact point at which the Sun releases the spacecraft and another force takes possession. The Sun's pull continues fading, while the combined influence of the stellar neighborhood and galaxy becomes relatively more important. The dominant description changes by degrees. Early in the passage, Voyager's motion can still be understood mainly as solar escape. Farther out, the Sun becomes one moving star among others. The spacecraft's path must then be described inside a changing field created by many masses, all moving through the galaxy. The idea of a single straight line becomes less complete with every increase in time. This does not mean Voyager is likely to make a dramatic turn while crossing the Oort cloud. Most gravitational influences at great distance are weak and slow. The spacecraft continues coasting, and its overall direction remains recognizable for a long time. But over thousands and millions of years, small changes matter. A faint pull acting across immense time can shift where the spacecraft later passes. The cloud therefore serves as more than the last distant region of the solar system. It is a transition between two ways of understanding Voyager. Inside the familiar system, its journey is measured outward from the Sun. Beyond the distant cloud, the useful landmarks become moving stars and the galaxy itself. Even the phrase, "leaving the Oort cloud," must remain qualified. Because its boundaries are broad, uncertain, and based on a changing population, the event will not happen on a single knowable date. Some distant objects may remain weakly attached to the Sun, while others are removed. The edge is better understood as a region where solar membership becomes increasingly fragile. What can be said confidently is the scale. Voyager's celebrated crossing into interstellar space occurred after decades of travel. Reaching the inner Oort region requires centuries. Passing beyond its broad outer reaches requires tens of thousands of years. Each step outward enlarges the timescale far more quickly than ordinary intuition expects. By the time Voyager completes that passage, Earth will have lost any practical connection with it. The spacecraft will have been silent for thousands of years. Its direction will still carry the history of Jupiter and Saturn, but the environment guiding its later motion will no longer be described mainly through the Sun. At that point, other stars become the obvious landmarks. One name appears often in accounts of Voyager's future: Gliese 445, a star the spacecraft will pass after tens of thousands of years. It is tempting to call that star Voyager's destination, the first harbor beyond the solar system. But the same emptiness that defines the Oort Cloud becomes even more severe between the stars. A close pass on an astronomical map can remain an enormous miss in physical space. Voyager will move near stars, but near will acquire a meaning no human journey has ever required. The sun's outskirts do not end with a collision, capture, or arrival. They fade into a larger gravitational landscape. After 30,000 years, Voyager may finally be beyond the broad region we associate with the Oort Cloud, but it will not have entered a place without structure. It will have exchanged one distant relationship for another. The next question is not whether Voyager keeps moving. It is whether any of the stars ahead can become more than a passing point of light. The first star commonly linked with Voyager's future is Gliese 445. It is often described as though the spacecraft were traveling toward it, creating the image of a final destination waiting beyond the solar system. But Voyager is not aimed at Gliese 445 in the way a mission is aimed at a planet. The spacecraft and the star are simply following paths that will bring them closer for a time. Predicting such an encounter requires more than extending Voyager's current direction across a fixed star chart. The stars themselves are moving. Some approach the sun, others recede, and all follow their own motion through the Milky Way. During the tens of thousands of years Voyager needs to cross interstellar distances, the stellar neighborhood changes shape. Researchers account for this movement by combining two kinds of information. Voyager's position and velocity come from its tracked trajectory and long-term calculations of its path. The Gaia mission measures the positions and motions of millions of stars. When these paths are carried forward together, scientists can estimate when a spacecraft and a star will pass most closely and how much distance will remain between them. The calculation is like following many travelers across a map whose scale is measured in light years. Each object has a starting position and a direction of motion. Carry those motions forward, and some paths draw nearer while others separate. But the result is not a photograph of the future. Every measurement contains a small uncertainty, and that uncertainty spreads as time is extended. Researchers therefore report likely approach times and distances, sometimes with ranges showing how the answer may shift. This is why a future flyby can be scientifically meaningful without being exact to a single year or a single final distance. For Gliese 445, the result is a future approach roughly 40,000 to 44,000 years from now. At that time, Voyager may pass within approximately 1.6 to 1.9 light-years of the star. The exact figures vary with the data and assumptions used, which is why the encounter is better expressed as a range than as a scheduled event. On a galactic map, a separation below 2 light-years can look close. In physical terms, it is still enormous. Light itself would need well over a year to cross the gap between Voyager and the star at their nearest approach. Voyager, moving far below light speed, would require many thousands of additional years to cover such a distance, even if its path turned directly toward the star. It will not. Gliese 445 is also moving toward the solar neighborhood. This matters because the encounter is produced by both objects moving, not by Voyager steadily chasing a stationary target. The star comes closer to Voyager's route as Voyager advances. Their paths briefly reduce the distance between them, reach a minimum separation, and then carry them apart again. There is no arrival. Voyager does not enter orbit around Gliese 445, cross its planetary system, or stop nearby. The star remains a remote point during the entire encounter. Calling it Voyager's destination turns a passing geometry into a mission that does not exist. Other predicted encounters make the same lesson even clearer. Calculations using Gaia data identify stars whose paths may bring them within a fraction of a parsec of Voyager during the next million years. One forecast produces a closest approach of about 0.3 parsec. That is closer than the Gliese 445 passage, but it still corresponds to roughly a light-year of separation. A light-year is not a near miss in any ordinary sense. It is an immense empty interval. The star may be the closest known object to Voyager at that time, and still remain far beyond any possible interaction involving its surface, planets, or immediate surroundings. The word closest describes a comparison with even greater distances. It does not mean physically close. The speed of these encounters also matters. Stars in Voyager can pass one another with relative velocities of tens or more than 100 kilometers per second. A slow, close approach could allow gravity more time to bend a path. A fast passage at a distance of a light-year gives the star very little ability to redirect Voyager. Its gravity reaches the spacecraft, but the effect is slight. Capture is more demanding than simple attraction. Every star pulls on nearby objects, yet an approaching spacecraft does not automatically fall into orbit. To become bound, Voyager would need to lose enough motion relative to the star. A distant, rapid two-body flyby normally bends a trajectory without removing the energy required for capture. No engine will perform a braking maneuver, and no known encounter brings Voyager close enough for a dramatic exchange. This separates three ideas that are often blended together. An approach means only that the distance between two moving objects decreases for a time. A deflection means gravity changes the direction or speed of one path by some amount. Capture means the object remains gravitationally tied to the star after the encounter. Voyager can experience the first and a very small amount of the second without experiencing the third. The star's pull never becomes zero, but at these forecast distances it is too weak and the passage too rapid to turn the spacecraft into a permanent companion. That difference determines whether a star becomes a landmark or a permanent home. This means the spacecraft's famous future flybys are important mainly as landmarks. They help us translate a nearly empty journey into moments that can be named. Instead of saying Voyager will cross interstellar space for hundreds of thousands of years, we can say it will pass nearer to particular moving stars at particular periods. The landmarks make the path understandable, but they do not give it a destination. They also reveal how empty the stellar neighborhood truly is. A spacecraft can travel for tens of thousands of years and still miss a star by more than the distance light covers in a year. It can continue for hundreds of thousands of years before achieving a somewhat smaller miss. The galaxy contains vast numbers of stars, yet the space available between them is greater still. There is an important limit to these forecasts. Gaia has transformed knowledge of stellar motion, but no catalog contains every object that might matter. Some stars are too faint, obscured, or lack complete velocity measurements. The farther calculations extend into the future, the more measurement uncertainty changes the predicted time and distance of an encounter. An unknown faint star could eventually be found to pass closer to Voyager than the encounters currently listed. Improved measurements could shift a predicted approach. This possibility prevents any catalog from being treated as a final schedule of everything Voyager will meet. But uncertainty in the list does not reverse the larger conclusion. Adding missing stars may change which object comes closest or when a passage occurs. It does not turn the stellar neighborhood into a crowded field. Most possible routes still cross enormous volumes in which direct encounters are rare. The useful distinction is between detail and structure. The detailed future list can change as observations improve. The structural fact remains that stars are widely separated. Voyager is small, and known approaches occur at large distances and high relative speeds. A particular flyby may be revised without making capture likely. Voyager therefore enters interstellar space without an obvious next home. It has enough speed to escape the Sun, but no predicted star waits to receive it. Its path passes through a moving population rather than from one fixed system directly into another. Yet the spacecraft is not free from gravity. Every distant star contributes a tiny pull. Gas, dark matter, and the mass spread across the Milky Way contribute as well. Individual stars may fail to capture Voyager, but together, the galaxy creates a gravitational field far larger than the influence of any one passing object. This is the next change in the meaning of Voyager's location. It will no longer be useful to imagine the spacecraft simply departing the Sun and missing a sequence of isolated stars. Its motion belongs inside the galaxy that contains them all. Gliese 445 is not Voyager's destination. Neither is any other currently known star. The larger destination, if that word can still be used, is not a point of light. It is an orbit within the Milky Way itself. Voyager has escaped the Sun, but it did not begin its journey from a place standing still inside the Milky Way. Long before launch, every atom in the spacecraft was already moving around the center of the galaxy, with Earth, the Sun, and the rest of the solar system. The gravity assists changed Voyager's motion relative to the Sun. They did not remove the much larger galactic journey it already shared. This distinction changes the meaning of its speed. The familiar figure of almost 17 kilometers per second describes Voyager moving away from the Sun. It is an added motion measured inside the solar system. It is not the spacecraft's complete speed through the galaxy. The Sun and its neighborhood travel around the galactic center at hundreds of kilometers per second. Voyager carries that broad motion with it. Its solar escape speed is therefore a smaller difference layered on top of the movement of the entire local system. From the Sun's viewpoint, the spacecraft races outward. From a galactic viewpoint, the Sun and Voyager continue traveling in broadly the same great circulation, while slowly separating from each other. That is why adding Voyager's present speed to a straight line and extending it forever gives the wrong picture. The line is drawn inside a frame that is itself curving around the galaxy. The spacecraft does not leave a stationary Sun behind while the Milky Way waits in front of it. Both objects are already falling through the galaxy's gravitational field. The Milky Way is not held together by a single central object in the way the solar system is dominated by the Sun. Its gravitational field comes from mass spread across the galactic disk, central regions, gas, stars, and a much larger distribution of unseen matter. Together, that mass creates a deep gravitational landscape. The Sun moves through it on a galactic orbit, and Voyager must do the same unless it gains enough energy to escape. Escape always depends on the system being escaped. Voyager had enough energy to avoid returning to a closed orbit around the Sun. Leaving the Milky Way demands far more. A useful comparison is an object leaving a small moon while remaining in orbit around the moon's planet. It has truly escaped one body, yet the larger gravitational system still contains it. Voyager's additional speed is far below what would be required to break free from the galaxy at its present location. No future engine burn is planned to supply the missing energy. The predicted stellar encounters are too distant to provide a powerful gravitational kick. Under the known path, Voyager remains bound to the Milky Way. Bound does not mean motionless or trapped near the sun. It means the spacecraft lacks the energy needed to travel away from the galaxy permanently. Voyager can move across enormous regions of the galactic disk. It can become separated from the sun by distances that make their present gap seem meaningless. It may pass through changing stellar neighborhoods and travel around the galactic center many times. Yet its path remains part of the galaxy rather than becoming a one-way departure into intergalactic space. This gives Voyager a new gravitational address. Its earlier address was the solar system because the sun governed the planets and the spacecraft began among them. After solar escape, no single nearby star becomes its home, but the Milky Way still provides a containing structure. The address is broad rather than precise. Somewhere on an orbit inside the galactic potential. That description may sound less satisfying than naming a destination, yet it expresses the physical relationship that lasts. A coordinate tells us where Voyager is at one moment. Binding tells us which system its future motion cannot easily leave. Across extreme time, the second statement can remain meaningful long after the first becomes uncertain. Solar escape therefore transforms into a new kind of orbit. Voyager is no longer a planet-following object or a spacecraft moving between known worlds. It becomes an extremely small independent body following the Milky Way's gravitational field. Its future resembles the motion of other unbound from a star objects that still remain bound to the galaxy. This galactic orbit will not look like a perfect circle drawn around the center. Voyager begins with much of the sun's circular motion, but its added speed and direction make its path slightly different. Relative to the sun and nearby stars, the spacecraft can drift inward or outward across the disk and move above or below its central plane. One way to describe this behavior is epicyclic motion. The word refers to smaller oscillations layered onto the larger orbit around the galaxy. Voyager and the Sun both circle the galactic center, but not along precisely identical paths. Their differences can make Voyager appear to wander across the solar neighborhood, separate from it, and later move through another part of the disk. The concept does not mean Voyager travels along a simple repeating loop that could be drawn exactly for all future time. It is a way of understanding the broad motion produced when an object's speed differs modestly from the local galactic flow. The galaxy supplies the main orbit. Voyager's solar escape creates the smaller difference within it. This is another reversal of the picture, created by a straight-line map. Relative to the Sun, Voyager continues outward and never naturally returns to a solar orbit. Relative to the galaxy, however, both the Sun and the spacecraft keep circling. Their separation can increase, change direction, and take them through very different regions without either object leaving the Milky Way. Scientists can explore this future by placing Voyager's measured position and velocity inside a mathematical model of the galaxy's gravitational field. A computer then follows how that field bends the path over long periods. Such integrations reveal possible broad routes across the galactic disk and show that Voyager remains gravitationally bound. These models are powerful because they replace a straight extrapolation with the forces that actually govern motion. They can show the difference between escaping the Sun and orbiting the galaxy. They can estimate how Voyager's position changes relative to the Sun over millions or billions of years. They can reveal large patterns that human intuition misses. But a model is not the galaxy itself. The real Milky Way contains structures that move and change. Its spiral arms are not rigid lines painted on a disk. Stars pass one another. Clouds and other concentrations of mass alter local gravity. The exact distribution of matter is not known perfectly, and it will not remain fixed. A simplified galactic model may represent the broad gravitational field while leaving out some changing structures. Its result should therefore be read as a scientifically informed path under stated assumptions, not as a guaranteed map of Voyager's exact future position. The longer the calculation runs, the more those assumptions matter. The model is strongest when answering broad questions. Does Voyager stay inside the galaxy? What general regions can its orbit reach? How does its motion differ from the Sun's? It is weaker when asked for an exact location at a date. The distinction protects the useful result without pretending the future galaxy is perfectly known. This limitation does not erase the central result. Details of the orbit can shift, while the larger conclusion remains stable. Voyager's speed is sufficient to escape the Sun, but insufficient to escape the Milky Way. Small disturbances may change where it travels inside the galaxy without easily giving it the enormous extra energy needed to leave. Individual stars, then, are not Voyager's permanent hosts, nor is the space between them an empty stage without gravity. The collective galaxy takes over the role once assigned to the Sun. It becomes the structure that bends the journey, defines the orbit, and provides the broadest useful answer to where Voyager belongs. The spacecraft once followed a path measured from planet to planet. Then it followed a path measured outward from the Sun. In its deeper future, the relevant motion is around the Milky Way. Each transition enlarges the system without ending gravity's control. Voyager is free of a closed solar orbit, but it is not free of the galaxy. Interstellar space is not a passage leading automatically into intergalactic space. It is part of the Milky Way itself. Once that is understood, the next scale becomes possible. Instead of asking which nearby star Voyager will approach, we can follow its broader galactic wandering. Over billions of years, the spacecraft may cross to regions far from the Sun and perhaps move through the solar neighborhood again. The question is no longer whether the galaxy holds Voyager, but where inside that galaxy its orbit may carry it. Once Voyager's motion is viewed as a galactic orbit, the future opens across a scale on which every familiar star pattern disappears. The constellations seen from Earth are temporary arrangements. Over thousands of years they distort. Over millions, their recognizable shapes dissolve. Over billions, the stars that formed them have traveled through entirely different regions or changed beyond recognition. Voyager moves inside that changing galaxy. Its path is no longer meaningfully described as a line aimed toward the constellation Ophiuchus, because the map behind that direction will not remain fixed. The useful question becomes how the spacecraft's orbit differs from the Sun's and where that difference may carry it over many circuits of the Milky Way. Models of the galactic gravitational field allow researchers to explore this question. They begin with Voyager's measured motion, add a mathematical representation of the Milky Way's mass, and calculate how the spacecraft and Sun may move over immense periods. In one such model, Voyager reaches the opposite side of the galactic disk relative to the Sun after roughly 1 to 2 billion years. Following both objects is essential. If only Voyager were calculated while the Sun remained fixed, the result would repeat the same error as the straight-line picture. The Sun completes its own galactic journey throughout the calculation. The model asks where Voyager is compared with that moving reference, not where it is compared with the solar system's present position. This turns opposite side into a relationship between two future orbits. It is not a permanent label attached to one region of the Milky Way. This does not mean Voyager travels straight through the center of the galaxy. Opposite side describes its position relative to the Sun after both have continued orbiting. Their slightly different galactic paths gradually separate them until they occupy widely divided regions of the disk. The result emerges from orbital drift, not a direct flight across a motionless Milky Way. 1 or 2 billion years is difficult to place beside the mission's present age. Voyager needed only decades to cross the Heliopause. It may need tens of thousands of years to pass through the solar system's distant outskirts. Yet even those spans are tiny beside the time required for its galactic motion to produce this much separation from the Sun. During that interval, Voyager can complete broad arcs around the galactic center while moving through changing neighborhoods. Stars that are currently nowhere near its path may become part of its future surroundings. Stars now close to the Sun will scatter along their own orbits. There is no lasting local group of familiar landmarks accompanying the spacecraft. The phrase, "far side of the galaxy," can also create a misleading image. It may sound like Voyager reaches a final outer shore and stops. In fact, there is no arrival. The spacecraft continues along its orbit. A position on the opposite side relative to the Sun is one phase in continuing motion, not an endpoint. Some model integrations carry the journey farther and suggest another surprising possibility. After roughly 3 to 4 billion years, Voyager's orbit may bring it through the broader solar vicinity again. The same orbital differences that separate the spacecraft from the Sun can later reduce their galactic separation. But return must be handled with care. It does not mean Voyager turns around. It does not mean it enters the solar system, passes Earth, or becomes captured by the Sun again. The solar vicinity on a galactic scale is an enormous region. Passing through it can still leave Voyager far beyond any practical contact or gravitational reunion. Even if the broad encounter occurred, nothing would restore the mission. Earth could not wait for a machine that had been silent for nearly the entire interval. The planets would not occupy their present arrangement at the predicted moment, and Voyager would not be navigating toward them. Return describes only a temporary reduction in galactic separation. It does not undo solar escape. The spacecraft would continue past the region just as it passes distant stars, coasting along an orbit whose direction was never designed to bring it home. The Sun will also have changed position during those billions of years. Voyager is not returning to a fixed address while the solar system waits. Both are traveling, and the model merely shows their paths occupying the same broad galactic region again. Their closest separation, timing, and exact geometry depend on the assumptions built into the calculation. By then, the Sun itself will be approaching a profound change in its life. The comparison matters because Voyager's galactic wander can last across a large fraction of the Sun's remaining stable existence. A trajectory set during a brief human mission may still be carrying the spacecraft through the disk when the system that launched it no longer resembles the one we know. This does not make the model a prophecy. The Milky Way used in a long-term calculation is necessarily simpler than the real galaxy. A model can represent the broad pull of the disk and other major components, but it cannot know every future movement of every star, cloud, and changing structure. Spiral arms are especially important to the limitation. They are not permanent solid lanes through which stars travel unchanged. Galactic structures evolve, and concentrations of mass can alter motion. A calculation that treats the gravitational field as smooth and stable captures the broad orbit while missing some disturbances that accumulate over time. Passing stars add another source of change. Most remain far away and produce only tiny effects, but a small deflection can matter after billions of years. A future encounter absent from the present catalog may shift where Voyager appears later in the model. The spacecraft can remain bound to the galaxy, while the details of its route become increasingly uncertain. The far-side result and possible return should therefore be treated as illustrations of what galactic binding permits. They show that Voyager can wander across the disk rather than simply moving outward forever. They show that two objects following different orbits can separate widely and later approach the same broad region again. They do not provide an exact schedule. Their real value lies in changing the scale of the question. At first, Voyager's future seemed to be a line extending from the Sun. The calculation replaces that line with a moving orbit woven through a moving galaxy. Whether each modeled crossing occurs exactly as shown is less important than the physical realization that Voyager's path curves, cycles, and remains contained. Voyager stays inside the galaxy. The distinction between a scenario and a prediction protects the value of the result. We do not need to know Voyager's precise future coordinates to understand that its path can span the galaxy. The model reveals the kind of motion available to an object with its measured speed, even if the actual location eventually differs. This is the largest spatial expansion of Voyager's story so far. Its journey began with distances between planets. It grew through the Oort Cloud and the gaps between stars. Now the relevant map is the galactic disk itself, and the clock advances by billions of years. Yet the spacecraft carries no awareness of these transitions. It will not observe the far side of the galaxy or recognize a return toward the Sun's wider neighborhood. Long before any billion-year orbit unfolds, Voyager's instruments will stop, its transmitter will fall silent, and its connection with Earth will end. That contrast separates two futures. The mission has a remaining lifetime measured in years. The object can have a dynamical lifetime measured across the age of stars. Voyager will spend almost all its existence not as an active explorer, but as matter continuing along a path established while it could still speak to Earth. Before following that silent object into deeper uncertainty, the story must return briefly to the present. The galaxy may hold Voyager for billions of years, but the power keeping it alive is already fading. Its next irreversible boundary will not be another place in space. It will be the end of communication. The billion-year journey belongs to Voyager as an object. Its life as an operating spacecraft is almost over. Voyager does not receive energy from sunlight at its present distance. Its electrical power comes from radioisotope thermoelectric generators. Inside them, radioactive material releases heat as it slowly decays. The generators convert part of that heat into electricity, allowing the spacecraft to run instruments, computers, heaters, and its radio system far beyond the practical reach of solar panels. The process has kept Voyager working for decades, but it cannot maintain the same output forever. The available electrical power falls by about 4 watts each year. That loss may sound small, yet every remaining system competes for an increasingly limited supply. After so many years, a few watts can decide whether an instrument remains active or must be switched off. The end of the mission is therefore not one sudden failure. It is a controlled narrowing. Engineers study the spacecraft's power, temperature, and condition, then make choices intended to preserve useful science and communication for as long as possible. Systems that once supported a wider mission can be turned off so that a smaller group of instruments continues operating. Each shutdown changes what Voyager can still sense. An instrument that falls silent removes one way of measuring the environment around the spacecraft. The mission continues, but with fewer channels connecting interstellar space to Earth. The surviving instruments become more valuable, precisely because the available power is disappearing. Power conservation also links systems that might appear separate. An instrument needs electricity to operate, but it may also depend on heaters keeping parts within a workable temperature range. The spacecraft must maintain enough orientation control to point its antenna toward Earth. Its computers and radio must remain capable of handling and transmitting the information. Saving one instrument, therefore, involves more than leaving a single switch on. Engineers must preserve a chain of functions, and every link draws from the same shrinking reserve. This careful management has already extended Voyager's work far beyond its original planetary encounters. The spacecraft was built to visit the outer planets, yet it continued into a new mission beyond the Heliopause. Its aging technology now measures a region that no earlier spacecraft had reached, using power produced by material carried from Earth in 1977. No exact date can be promised for the final transmission. The generators decline predictably, but the spacecraft's remaining systems do not follow a perfect schedule. An instrument may last longer than expected. A component may fail. Engineers may find another way to save power, or an unforeseen problem may shorten the mission. Current projections place the end of useful communication somewhere in the early to mid-2030s. That is a window, not an appointment. There may be a final scientific measurement before the final engineering signal. There may be a period when little remains except basic information showing that part of the spacecraft still operates. Earth will also experience the ending late. By then, every signal from Voyager will require almost a full day to cross the distance home. If a system fails aboard the spacecraft, controllers cannot know immediately. The evidence begins traveling toward Earth at light speed, while the spacecraft continues moving. When a command is sent in response, it requires another long crossing. Controllers must wait for the instruction to arrive, and then wait again for any reply. Near the end of the mission, every attempt to diagnose or preserve a failing system will unfold across a conversation measured in days. At some point, a carrier signal may arrive for the last time. It may contain science, engineering data, or only the evidence that the transmitter still has power. Earth may send another command and hear nothing back. But silence will not immediately reveal why Voyager stopped responding. The transmitter may lack power. Another system may have failed. The spacecraft may no longer point its antenna accurately enough toward Earth. The people listening may not know at first that the ending has occurred. A missing signal can invite another attempt, another carefully prepared command, and another wait across the distance. Only after repeated silence would the practical conclusion become unavoidable. Even then, Earth could identify the end of contact without seeing the condition of the machine. The last received message would describe Voyager as it was almost a day earlier. By the time that message reached us, the spacecraft would already have moved beyond the moment it recorded. There will probably be no single dramatic moment aboard Voyager. No observer will be present when the last active system stops. The spacecraft has no awareness of its power declining and no understanding of the silence that follows. It does not experience death, loneliness, or loss. Those meanings belong to the people who built, operated, and listened to it. For the machine, the change is physical. Electrical power becomes insufficient. Instruments stop measuring. The computer can no longer carry out useful operations. The radio no longer sends information across the gap. Operationally, Voyager then stops being a spacecraft in the active sense. It no longer explores by gathering knowledge and returning it to Earth. It cannot report where it is, describe what surrounds it, or respond to commands. Its mission ends even though its motion does not. After that, Voyager will carry no fresh testimony back to the world that made it, even while its ancient trajectory continues without interruption onward. At the instant the final signal is lost, gravity does not change. Voyager does not slow or turn. The path produced by its launch, planetary encounters, and later gravitational influences continues. The silent machine crosses the same space it would have crossed if its transmitter still worked. This separates mission lifetime from material lifetime. The mission depends on power, functioning electronics, communication, and people capable of receiving the data. The object needs none of those things to continue existing. As long as it is not destroyed or captured, it remains a piece of matter moving through the galaxy. Calling Voyager inert does not mean it remains untouched. Radiation continues striking its surfaces. Tiny particles may leave marks. Materials change across extreme time. Temperatures and local environments vary as the spacecraft moves through different regions. But the outline of that damage cannot be predicted confidently across trillions of years. It is possible that much of the spacecraft remains recognizable for an extraordinary period because direct impacts are rare. It is equally important not to turn that possibility into a claim of perfect preservation. Components can degrade, surfaces can be weathered, and the detailed condition of the golden record, after such immense time, is unknown. The record may remain physically attached while becoming altered. The spacecraft may remain macroscopic while delicate details are damaged. Existence, intactness, and readability are three different claims. Evidence supporting one does not automatically prove the others. This boundary is especially important because Voyager's silence removes the only direct source of new information about its condition. While radio contact continues, engineers can learn about power, orientation, and surviving systems. After contact ends, every statement about the spacecraft's state becomes an inference based on physics, past data, and models. Voyager will then spend almost its entire future unobserved. Decades of communication will be followed by thousands, millions, billions, and perhaps trillions of years without a report. It may cross the galaxy many times, but none of those passages will be witnessed through its instruments. The contrast is difficult to avoid. Human beings designed Voyager to gather information, and for a brief period it turned distant places into signals that Earth could understand. Its longest existence, however, begins when that exchange is over. The explorer becomes an artifact. The final signal will not mark the end of Voyager's journey. It will mark the end of our ability to follow that journey directly. From then on, the question, "Where is Voyager?" can be answered only by calculation. At first, that calculation can remain accurate, but every unknown force, missing object, and tiny uncertainty has more time to affect the path. The farther Voyager moves into the future, the wider the range of possible positions becomes. The last signal, therefore, creates a new kind of distance. Voyager is not only far from Earth in space, it becomes separated from observation itself. The galaxy continues carrying it, but the map begins to depend entirely on what our models can preserve. For the near future, Voyager's position is not a mystery. Decades of tracking have established its path, and calculations can predict where it will be well enough for Earth to aim radio signals toward it. The spacecraft's motion follows physical laws. Nothing about its silence will cause those laws to stop working. The difficulty comes from the length of time placed between the measurement and the answer. Every measurement has a limit. Voyager's position and velocity are known with great accuracy, but not with infinite accuracy. The location and motion of every star are also measured with some uncertainty. The galaxy's mass is mapped through observations and models, but no map contains every detail. Over a short interval, these small limits barely affect the result. Two calculations beginning with slightly different acceptable values may still place Voyager in almost the same region. Mission navigation works because the forecast period is short enough and the available information is precise enough for the purpose. Extend the same calculation across thousands or millions of years, and the possible paths begin to separate. A tiny difference in starting speed changes the distance traveled. A small uncertainty in direction moves the spacecraft sideways from the expected line. A weak gravitational pull acts for longer. None of these effects needs to be large at first. Time enlarges their consequences. Passing stars create a deeper problem. Current catalogs identify millions of stellar motions, but they do not contain every faint, hidden, or poorly measured object. A star missing from the calculation may pass near enough to alter Voyager's path slightly. Even if the encounter is far too distant for capture, the small deflection can shift the spacecraft's later position. After the deflection, every following prediction begins from a changed path. A second encounter then occurs under different geometry. The effects build in sequence. The uncertainty is not merely added once, it changes the conditions under which later changes occur. The galaxy itself also evolves. A simple model may represent its broad gravitational field as smooth and stable, but the real Milky Way contains moving structures. Stars rearrange. Clouds and concentrations of mass travel through the disk. Spiral patterns change. The distribution producing the gravitational field at one time will not be identical billions of years later. No observer today can provide a complete map of those future changes. A computer can calculate the consequences of the assumptions it is given, but it cannot recover information that was never measured or predict every alteration in a complex galaxy across trillions of years. This is sometimes described through the idea of chaos. In this context, chaos does not mean that motion has no cause or that Voyager suddenly behaves randomly. It means that small differences in initial conditions can eventually produce very different detailed outcomes. The laws remain orderly, while precise long-term prediction becomes impossible. The distinction matters because unpredictable is often mistaken for anything can happen. That is not the case. A dropped object may have an uncertain landing point while still being certain to remain near Earth. In the same way, Voyager can have an uncertain position along a future galactic path without gaining permission to appear anywhere in the universe. Physical limits still narrow the possibilities. The uncertainty grows inside those limits, and strong constraints can survive even when fine detail is gone. Imagine two models of Voyager that begin almost identically. For a time, their paths overlap. Later, one version passes slightly nearer to a star and receives a somewhat stronger deflection. That difference changes the next region it enters. After enough encounters and enough galactic motion, the two calculated positions may be widely separated even though both models began within the uncertainty of the original data. Adding more computer power cannot fully solve this problem. A faster calculation can follow a model with greater detail, but it cannot make present measurements infinitely exact. It cannot list future objects that remain unknown. It cannot guarantee that a simplified representation of the galaxy will match every structure that later develops. This does not create one exact date when the map suddenly stops working. Predictive confidence fades by degrees. Near-term coordinates can be narrow and useful. Farther ahead, the possible region grows. Eventually, asking for a single point gives a false impression of knowledge that the evidence no longer supports. The correct response is not to abandon the question, but to change the kind of answer. Instead of one coordinate, scientists can describe a range of possible positions. Instead of claiming an exact encounter, they can estimate encounter rates and probabilities. Instead of drawing one guaranteed orbit, they can identify which broad outcomes are compatible with Voyager's known energy and environment. Some conclusions survive longer than detailed coordinates because they depend on large differences rather than tiny ones. Voyager is far below the speed needed to escape the Milky Way under ordinary conditions. Small measurement errors do not erase that energy gap. A distant stellar deflection may shift its galactic orbit without immediately throwing it into intergalactic space. The difference can be expressed as precise position versus gravitational membership. We may lose the ability to say where Voyager is along its orbit, while retaining strong reasons to believe the orbit remains inside the galaxy. We may not know which stellar remnant lies nearest to it, yet still conclude that a direct collision is unlikely. This statistical knowledge is real, but it must remain qualified. Encounter rates depend on how densely objects are distributed and how that density changes. Galactic binding depends on the future gravitational structure and on whether a rare strong event adds enough energy for escape. The estimates describe what is overwhelmingly expected under stated physical assumptions, not what is guaranteed under every possible history. Confidence, therefore, forms layers. The present trajectory is supported by direct tracking. Near-future stellar approaches are modeled from measured motions. Billion-year galactic paths show broad possibilities within simplified potentials. Trillion-year statements describe likely classes of outcome rather than locations. An honest documentary must preserve those layers instead of blending them into one voice of certainty. A direct measurement can be stated firmly. A model result needs its assumptions. A statistical estimate needs its range and limitations. An unknown should remain unknown. This does not weaken the story. It allows the final answer to carry the exact weight of the evidence supporting it. Each layer answers a different question. Direct tracking tells us where to point an antenna. Flyby calculations identify probable future landmarks. Galactic models show why Voyager remains part of the Milky Way. Far future statistics tell us what kinds of events are likely or rare after exact history has been lost. The honest map becomes less detailed as it extends farther into time. Names disappear first, then exact paths, then narrow regions. What remains is a gravitational address and a set of probabilities. Voyager is somewhere inside an evolving bound system, following one history among many histories that current measurements cannot distinguish. The map loses sharpness, but it does not become blank. Broad boundaries remain visible, even after the precise route has disappeared entirely from scientific reach. This is not a failure of physics, it is a boundary on information. To calculate one exact path after 10 trillion years, we would need impossibly complete knowledge of Voyager's starting state and every influence it encounters, along with an exact description of how the galaxy changes throughout the interval. The title's question, therefore, contains its own correction. Science cannot responsibly name Voyager's precise coordinates after 10 trillion years. It can still ask what environment surrounds it, what forces probably hold it, whether it is likely to have struck anything, and what physical state is plausible. Those questions now lead beyond the bright Milky Way we know. 10 trillion years is not merely a longer version of the present. By then, the population of shining stars and the structure of the galactic environment will have changed profoundly. To locate Voyager as honestly as possible, we must first understand what remains of its galaxy after the age of ordinary starlight has nearly ended. 10 trillion years from now, Voyager will not be moving through the Milky Way we see today. The broad force holding it may remain, but the bright population, revealing the galaxy's shape, will have changed almost beyond recognition. The Sun will be long gone from its present form. Earth and the familiar solar system will no longer provide a meaningful home toward which Voyager could return. The star that launched the spacecraft's civilization occupies only a small opening moment in the journey now being considered. Other stars survive much longer. The smallest red dwarfs consume their fuel with extraordinary patience. Their low mass allows them to shine for trillions of years, far beyond the lifetime of stars like the Sun. At the tidal's horizon of 10 trillion years, some of the longest-lived stars may have only recently approached the end of their luminous existence, depending on their mass and the boundaries used for the stellar era. The future, therefore, does not change from a bright galaxy to complete darkness on one date. Starlight fades gradually, as generations of stars exhaust their fuel, and fewer new stars form. Large, bright stars disappear first. Smaller stars remain. Eventually, ordinary shining stars become rare, and the galaxy is increasingly populated by what those stars leave behind. White dwarfs are the compact remains of stars that shed their outer layers. Neutron stars and black holes remain after more violent stellar endings. Brown dwarfs, too small to sustain ordinary hydrogen fusion like true stars, continue as faint bodies. These objects can persist after the familiar age of starlight has nearly ended. The future galaxy is therefore not empty. It is dark, because much of its mass no longer shines brightly. Gravity does not require visible light. A white dwarf, neutron star, black hole, or cold object still contributes to the gravitational structure even when it cannot illuminate Voyager's surroundings. From a distance, such a system would be difficult to recognize by the standards used for the present Milky Way. Its familiar bands of starlight would no longer trace the same structure. For an object moving inside it, however, the unseen mass would continue shaping every orbit. Voyager does not need bright stars to define a path. It needs only the gravitational field created by what remains. By this time, the Milky Way may no longer exist as a separate spiral galaxy. Its long interaction with Andromeda is expected to reshape both systems into a merged remnant. The exact appearance and internal arrangement of that remnant cannot be carried reliably across trillions of years. Its broad gravitational binding is more defensible than any detailed future picture. Calling the remnant Milkometa can provide a convenient name, but the name should not suggest a fixed object whose final form is known. Stars and remnants continue orbiting, passing, and slowly exchanging energy. The system evolves long after the visible merger is complete. Nor should the merger be treated as one collision in which every star strikes another. Galaxies contain far more open space than stellar material. Their large-scale forms can combine, while individual objects mostly continue through changing gravitational fields. Voyager's fate is therefore determined less by a crowded impact than by the remaking of the broad system in which it orbits. Voyager would be one of countless small objects moving through that changing structure. It would not orbit the center along the same path predicted by a model of today's Milky Way. Every earlier perturbation and every later change in the merged system would have altered its detailed route. Yet the spacecraft would still most likely remain within the gravitational territory produced by the remnant. The expansion of the universe, does not automatically pull Voyager away from this bound system. Cosmic expansion is most important across the great distances, separating structures that are not held together strongly enough by gravity. Inside a bound galaxy, or merged local remnant, gravity can continue controlling the motion of its members under the standard picture. This distinction prevents another misleading straight-line image. Accelerated expansion does not act like a wind pushing Voyager outward from every nearby mass. It changes the large-scale separation of unbound regions. A spacecraft already held within a galactic gravitational system continues responding mainly to that local system. The wider universe may become increasingly inaccessible as distant, unbound galaxies recede. Voyager's local environment, however, remains a collection of remnants, low-mass objects, and diffuse matter tied together gravitationally. Its cosmic surroundings grow darker without becoming structureless. That difference is essential at 10 trillion years. If every distant object simply followed cosmic expansion away from every other object, Voyager's address would dissolve. In the standard picture, the local remnant keeps an address because its members share a bound gravitational history. The system changes internally while remaining separate from the expanding distances beyond it. For Voyager, darkness also has no observational meaning. The spacecraft will have no functioning camera, detector, or transmitter capable of reporting the change. Describing the remnant as dark tells us about the environment, not about an experience aboard the machine. Its passage through that environment may be almost entirely uneventful. The volume between remnants remains immense. Most orbits do not lead directly into another object. Voyager can continue crossing the system while passing nothing closely enough to stop or destroy it. Yet this is still a statement of probability. Over trillions of years, the galactic remnant evolves through many weak gravitational encounters. Objects exchange energy. Some move onto different orbits. A rare strong passage could alter Voyager's path. On still longer timescales, gravitational systems can gradually lose members. The question is whether such processes are likely to remove Voyager before the title's 10 trillion year point. The available evidence suggests that its lack of galactic escape energy continues to matter. A dramatic ejection requires an uncommon event capable of giving the spacecraft a much larger change in motion than ordinary distant encounters provide. The exact orbit is lost, but the broad environment remains constrained. Voyager is not expected to be near the present Sun, because the Sun no longer exists in that form. It is not expected to be traveling through today's spiral arms, because those structures have changed. It is not expected to be approaching a named modern star, because the stellar map has disappeared. The strongest broad description is that Voyager moves somewhere within the dark gravitational remnant of the galaxy and its local merged system. Around it are likely to be stellar remnants and faint bodies, rather than a sky filled with ordinary shining stars. Its location has become an address without coordinates. This is the setting required for the title's answer. The date does not place Voyager at a recognizable landmark. It places the spacecraft in a changed era of matter, after the Sun, near the far edge of ordinary stellar lifetimes, and inside a system whose gravity lasts longer than its light. This future is ancient beyond human measure, yet it remains earlier than many even more remote cosmic processes that do not belong in Voyager's 10 trillion year answer at all. The remaining question is no longer what the future galaxy looks like. It is what has probably happened to Voyager inside it. Has the spacecraft struck anything? Has it escaped? Could any part of it remain recognizable? And how confidently can each answer be stated? Those questions bring every earlier scale together. The solar escape, distant stellar misses, galactic binding, loss of communication, and collapse of exact prediction now point toward one final scientific conclusion. After 10 trillion years, the easiest facts to state are the facts that ended first. Voyager 1 will have no electrical power. Its instruments will not be operating. Its transmitter will not be calling toward Earth, and no computer aboard it will be choosing a new destination. The spacecraft will not be an explorer in any active sense. It will be matter following gravity and motion. That conclusion is close to certain because the mission's power supply declines across decades, not trillions of years. Whatever uncertainties surround the far future, no known engineering system aboard Voyager can bridge the title's timescale. Its active life occupies an almost invisible fraction of its possible material existence. The next conclusion is less exact, but still strongly supported. Voyager will most likely remain somewhere inside the evolved gravitational remnant of the Milky Way and the local merged system. It escaped the Sun, but it never possessed the energy needed to escape the galaxy. Ordinary distant encounters can shift its orbit without supplying the enormous change required to eject it. By 10 trillion years, the familiar map has vanished. There is no scientifically responsible way to name Voyager's coordinates, identify a modern constellation around it, or point to one exact location in the remnant. The spacecraft will have followed many changing galactic orbits through a system repeatedly altered by stellar motion and long-term evolution. Its address can therefore be stated only broadly. Inside the gravitationally bound remnant, moving among faint bodies and stellar remains. The statement identifies what probably contains Voyager, not where it sits at one moment. Within that address, Voyager may have occupied many very different regions. It can pass nearer the center of the remnant during one period and farther through its outer territory during another. It can move above or below whatever disk-like structure survives. None of these possibilities changes the larger relationship. Wherever Voyager happens to be along its uncertain path, the remnant's gravity remains the most likely system organizing that motion. That may appear to avoid the title's question, but it is the strongest form the evidence allows. A false coordinate would be more specific and less true. The galactic address survives because it depends on Voyager's energy and the broad structure holding it. The exact point fails because it depends on every small event along the path. The next question is whether Voyager survives those events at all. 10 trillion years provides an almost unimaginable number of opportunities for something to happen. The spacecraft crosses changing neighborhoods, passes remnants, and continues through a system filled with objects. Human intuition may therefore expect an eventual collision to be unavoidable. The available statistical estimate produces the opposite result. The characteristic timescale for Voyager to collide with a star, or, in the later galaxy, a stellar remnant, is of the order of 10 to the 20th years. Written out, that is roughly 100 quintillion years. This number is not a predicted collision date. It does not mean Voyager travels safely until one exact future year and then strikes something. A characteristic timescale summarizes an extremely low probability across a population and environment. Individual histories can differ. A collision could occur earlier, or the spacecraft could avoid one much longer. The value is useful because of the scale it reveals. 10 trillion years is 10 to the 13th years. The collision estimate is around 10 to the 20th. 7 powers of 10 separate them. The title's horizon is therefore about 10 million times shorter than the characteristic weight implied by that estimate. The comparison also explains why ordinary intuition fails. On Earth, long time usually increases the chance that a moving object eventually meets an obstacle because our surroundings are crowded. Voyager crosses a very different environment. Extending the journey adds opportunities, but each opportunity remains extraordinarily small. The spacecraft presents a tiny target. Stars and remnants occupy only a minute fraction of galactic volume, and most apparent approaches preserve enormous separation. Time is vast, but the emptiness it acts across is vaster. Even after the last long-lived stars have approached darkness, Voyager is still expected to be far earlier than the timescale associated with striking one. Trillions of years do not make the galaxy crowded. They expose how difficult it is for one small spacecraft to hit one small target inside such a vast volume. This produces one of the strongest parts of the answer. Voyager will probably not have collided with a star or stellar remnant by 10 trillion years. It may never have passed close enough to any large body for a dramatic gravitational event. Its journey can remain uneventful, not because the spacecraft is protected, but because most of its environment is separation. The result is survival by absence rather than strength. Voyager was not built to endure 10 trillion years, but the galaxy may offer so few direct encounters that extraordinary endurance becomes the most probable outcome despite the spacecraft's ordinary materials. Probability is not certainty. The collision estimate depends on assumptions about the density and evolution of the galactic system. A rare encounter absent from present knowledge could change the outcome, but no evidence supports presenting impact as the expected fate by the title's date. Avoiding a major collision does not guarantee perfect preservation. Voyager is exposed to radiation, tiny particles, and the slow alteration of materials. Across 10 trillion years, small forms of weathering have more than enough time to accumulate. No complete physical model can tell us the condition of every component at that horizon. The spacecraft may remain macroscopic, an object whose main structure still exists rather than having been shattered by a direct impact. That possibility is supported by the same emptiness that makes collisions rare. But macroscopic survival is not the same as remaining intact in the everyday sense. Surfaces may be scarred. Materials may become brittle, altered, or eroded. Parts may separate. Fine structures can be damaged even while the overall object persists. A shape recognizable as human-made might survive without preserving every feature in its original condition. The golden record requires even greater care. It may remain attached to the spacecraft, or it may be altered along with the structures holding it. Its surface may preserve some patterns while losing others. There is no strong basis for claiming that it will be perfectly readable after 10 trillion years. Existence, attachment, and readability must remain separate. Voyager can survive as a macroscopic artifact while the record becomes damaged. The record can remain physically present without any recipient finding it, and even if found, its condition may not permit its information to be recovered as intended. Another alternative is ejection from the galactic remnant. Over very long periods, repeated gravitational encounters can redistribute energy among objects. Some members of a system can eventually gain enough motion to escape. A rare strong encounter could, in principle, send Voyager into intergalactic space. But this possibility should not be confused with the expected outcome by 10 trillion years. Voyager begins deeply below galactic escape speed. The known stellar approaches are distant and fast. Ordinary perturbations change its orbit far more easily than they remove it from the entire system. Ejection remains possible, not probable at the title's horizon. Voyager was built to work for years, not to remain meaningful for trillions of them. Its designers created a machine that could cross the outer solar system, survive radiation, operate far from the sun, and send discoveries home. Every working part belonged to a practical mission with limited power and a human team waiting for its signals. Its longest future begins after all of that has ended. Once the transmitter falls silent, Voyager no longer performs the purpose for which it was built. It gathers no usable science. It receives no command. It returns no image or measurement. Yet the same object may continue moving for a span that makes its active mission almost vanish. That endurance was not engineered in the ordinary sense. Voyager was not tested for 10 trillion years, and no component was guaranteed to remain unchanged across the age of stars. Its possible longevity comes mainly from its surroundings. There is almost nothing close enough to strike it. The emptiness that separated Voyager from every destination becomes the condition that may preserve it. A crowded environment would destroy or capture the spacecraft far sooner. Interstellar and galactic space offer no shelter, but they offer distance. Survival emerges from absence. Attached to this accidental deep-time artifact is the Golden Record. It was created as a message from Earth, an attempt to place sounds, images, and signs of human life aboard a spacecraft leaving the planets. The record gives Voyager a second role beyond measurement. It does not merely travel from Earth, it carries evidence of what Earth contained. The message was made for a possible finder, not a promised one. Nothing in Voyager's predicted path suggests that discovery is likely. The spacecraft misses known stars by enormous distances, and the chance of meeting any small object remains tiny. A message can be sincere even when delivery is uncertain. 10 trillion years deepens that uncertainty. The record may remain attached, damaged, altered, or unreadable. Its physical survival cannot be assumed from the probable survival of the spacecraft's main structure. Fine information is more vulnerable than the broad existence of an object. Even perfect preservation would not guarantee understanding. A finder would need to recognize the record as an artifact, recover its information, and interpret the choices made by minds from a world long gone. Physics can carry the object. It cannot promise an audience. This boundary protects the Golden Record from becoming a comforting legend. Voyager is not certain to deliver humanity's story to another civilization. It may never enter a planetary system. It may never pass close enough to be noticed. Its message may travel for longer than stars shine without being read once. That possibility does not make the gesture empty. The record expresses a decision made while Voyager could still be touched, built, and directed. Human beings knew the spacecraft would leave every practical reach of their world, and they placed something aboard it that spoke beyond the needs of navigation. The meaning belongs to that decision, not to a guaranteed result. The record says that when a path opened beyond the known planets, people chose to send more than instruments. They sent a description of themselves, incomplete and shaped by their moment, into a future they could not control. That act does not prove humanity expected to be remembered. It shows that people understood the difference between gathering knowledge and leaving evidence. Voyager's instruments turned distant environments into information for Earth. The record turned information from Earth into an object moving outward. One mission looked back through radio. The other looked forward, without knowing whether anyone would ever look back. Both were carried by the same spacecraft, but only one could continue after the power failed. Voyager cannot value that choice. It does not remember Earth. It cannot know that the sun disappears or that the galaxy grows dark. It does not feel the distance between itself and every living thing that once communicated with it. Calling Voyager alone must therefore remain a human description. The spacecraft experiences nothing. Its solitude is measured by the end of contact, the absence of a chosen destination, and the low probability that another object will ever come close enough to interrupt its path. At first, the word alone may sound like sadness projected onto a machine. After following the science, it becomes something more precise. Voyager is alone because relationships that once defined it have ended. It is no longer connected to Earth by working radio. It is no longer moving inside the Sun's planetary family. It is not captured by another star. It remains an object between systems, held only by the broad gravity of the galactic remnant. Yet the spacecraft is never outside physical history. Its materials came from Earth. Its path records the gravity of Jupiter and Saturn. Its direction preserves choices made by engineers. Damage accumulated across time records encounters with radiation and dust. Even without a witness, the artifact remains a consequence of a particular world. If some future observer ever found Voyager, the discovery would not reveal humanity as we are now. It would reveal that humanity once existed, and once reached far enough to place an object on an interstellar path. The record would be a fragment, not a complete account. If nobody finds it, Voyager still changes what happened in the universe. Matter shaped by life left one planetary system and entered a galactic orbit. The change may be tiny compared with a galaxy, but it is real. A civilization briefly acquired the ability to send an artifact beyond its star's wind. This does not make Voyager eternal. Rare impacts remain possible. Materials can decay. Galactic encounters may eventually eject or destroy it. On timescales beyond the title's horizon, processes continue that no artifact can be promised to survive. 10 trillion years is not forever. It is simply long enough to transform the meaning of the mission. The active spacecraft lasts for decades. The silent object may outlast Earth's habitability, the Sun's familiar life, and nearly the whole age of ordinary stars. The contrast returns us to the signal with which the journey began. In the present, Earth can still send a command toward Voyager. The message crosses more than 25 billion kilometers and arrives almost a day later. Voyager may respond, and another signal begins the long return. That delay already feels like separation, but it still contains a relationship. A transmitter sends, a receiver listens. Engineers wait, because an answer remains possible. The empty hours between command and reply are filled with expectation. When the final signal ends, the same distance acquires a different meaning. Earth may transmit, but no working system aboard Voyager can answer. The communication path remains open in physics while becoming useless in practice. Light can cross the gap, yet conversation has ended. After Earth and the Sun are gone, even that one-way act becomes impossible. No station remains to point an antenna. No listener remembers the frequency. Voyager continues without a radio relationship to its origin. But the message aboard it does not travel like the radio signal. A signal leaves Earth, crosses space, and disappears into noise after passing its destination. The golden record remains with the spacecraft. Its motion is the transmission. Every galactic orbit carries the physical message farther through time, even when it carries it nowhere likely to be found. The record does not need power to keep moving. It does not need an active antenna. Gravity becomes the only delivery system, and the dark remnant of the galaxy becomes the route. There may be no receiver at the end, because there may be no end in the ordinary sense. Voyager does not approach a final mailbox. It circles, wanders, and survives for as long as chance and matter allow. The opening image was a command needing almost 1 day to reach the spacecraft. That was distance, measured through waiting. 10 trillion years later, waiting has lost its meaning because nobody remains in the conversation. What remains is not a voice calling through space. It is a cold object carrying the memory of a voice in physical form. Across the dark remnant, its motion becomes the last form of connection between the artifact and its vanished makers. Voyager began as a machine that sent its discoveries home. It may end as a message whose home no longer exists.